Every memory you've ever formed, every face you've remembered, every moment that made you who you are, all of it exists in a structure inside your brain that scientists thought they understood until 3 days ago. What they found hidden inside your hippocampus changes everything we believed about memory, identity, and why some people lose themselves to diseases like Alzheimer's while others don't. The discovery reveals that your brain isn't just storing memories, it's organizing them in invisible layers that determine which moments stay with you forever and which ones vanish without a trace. Inside your skull, tucked deep within the temporal lobe, sits a small, curved structure called the hippocampus. For decades, neuroscientists have known this region plays a critical role in converting experiences into long-term memories. It helps you navigate through space, recognize faces, and recall the emotional weight of moments that shaped your life. But here's what they didn't know. The hippocampus isn't organized the way we thought. On December the 6th, 2025, researchers at the University of Southern California published findings in Nature Communications that shattered our understanding of this memory center. Using advanced RNA imaging techniques, they mapped over 330,000 genetic signals from tens of thousands of neurons in the hippocampal CA1 region. What they discovered was astonishing. 4 distinct continuous layers of nerve cells, each with its own molecular signature, stacked like geological strata inside your brain. Think about that for a moment. Your memories aren't just floating around randomly in your head. They're organized in precise hidden layers that run the entire length of your hippocampus. Each layer is defined by unique patterns of active genes, and each one processes different aspects of your experience. When you remember your first kiss, when you navigate back to your childhood home, when you feel the rush of emotion tied to a song, different layers of your hippocampus are lighting up, working in concert to reconstruct the past. And here's the unsettling part. These layers aren't evenly distributed. They shift and change in thickness along the hippocampus, meaning that some parts of this structure contain more of one cell type than another. This shifting architecture explains why certain memories feel more vivid, why some experiences scar you forever, and why others fade as if they never happened. But the implications go much deeper than memory alone. The researchers found that this 4-layer structure may explain why certain neurons in the hippocampus are more vulnerable to neurodegenerative diseases. In Alzheimer's, for example, the hippocampus is one of the first regions to deteriorate. Patients lose recent memories first, then older ones, and eventually they lose the ability to form new memories altogether. The disease doesn't attack the brain randomly, it targets specific types of neurons. And now, with this new discovery, scientists understand why. If a disease targets the cell type found in one of these 4 layers, the damage will vary depending on where in the hippocampus that layer is most prominent. It's like watching a geological fault line crack open. Certain layers are more fragile than others, and when they break, entire networks of memory collapse. Let's go deeper into what this means for your sense of self. Philosophers have long debated the nature of personal identity. Are you the same person you were 10 years ago? What makes you you if every cell in your body has been replaced multiple times over? The answer, it turns out, lies in the continuity of your memories. Your identity is a story your brain tells itself, stitched together from fragments of experience, emotion, and sensory detail. And that story is written in the architecture of your hippocampus. The 4 layers discovered by the USC team aren't just passive storage units. They're active processing systems. Each layer connects to different brain regions, receiving input from areas responsible for sensory perception, emotional regulation, and spatial awareness. When you experience something, All four layers work together to encode that moment into a memory. But not all memories are created equal. Consider trauma. Why do traumatic memories feel so different from ordinary ones? Why can a single smell or sound transport you back to a moment of terror with vivid, overwhelming clarity? The answer lies in how your hippocampus encodes these experiences. Traumatic events trigger a cascade of stress hormones, cortisol, adrenaline, that flood your brain. These chemicals amplify the activity of certain neurons in your hippocampus, burning the memory into your neural architecture with exceptional intensity. The four-layer structure means that this amplification doesn't happen uniformly. Some layers may encode the emotional weight of the trauma, while others capture the sensory details, and still others anchor it in time and space. This is why trauma survivors often report feeling like the event is happening again in the present. The memory isn't just a recollection, it's a full sensory reconstruction, powered by the layered architecture of the hippocampus. Now, let's talk about forgetting. We often think of forgetting as a failure, a flaw in the system. But forgetting is actually one of the brain's most important functions. If you remembered every single detail of every single moment, your mind would be overwhelmed with irrelevant information. The brain has to decide what to keep and what to discard, and that decision is made, in part, by the four layers of the hippocampus. Recent research in neuroscience has shown that memory consolidation, the process of transferring short-term memories into long-term storage, happens during sleep. While you're unconscious, your hippocampus replays the day's experiences, strengthening the neural connections associated with important events and letting weaker ones fade. The layered structure discovered by the USC team suggests that this process is far more sophisticated than we realized. Each layer may prioritize different types of information, filtering out the noise and preserving what matters most. But here's where it gets existentially unsettling. If your sense of self is built on memory, and memory is organized in layers that selectively preserve certain experiences while discarding others, then who you are is not a complete record of your life. It's a curated collection of moments, filtered through the architecture of your brain. You are not the sum of everything you've experienced. You are the sum of what your hippocampus decided was worth remembering. And if those layers degrade, if disease or injury disrupts their function, the story your brain tells about who you are begins to unravel. This is the horror of Alzheimer's. It's not just memory loss, it's the disintegration of the self. Patients forget their loved ones, their achievements, the defining moments of their lives. They become strangers to themselves, adrift in a present disconnected from the past. The discovery of these four layers also raises profound questions about the nature of consciousness. Neuroscientists have long debated where consciousness comes from. Is it a product of the brain's electrical activity? A byproduct of complex information processing? Or something more fundamental? The hippocampus doesn't generate consciousness, but it plays a critical role in creating the continuity of conscious experience. Without it, you wouldn't be able to connect one moment to the next. You'd exist in an eternal present, unable to learn from the past or plan for the future. The four-layer structure suggests that this continuity isn't a single unified process. It's the result of multiple systems working in parallel, each contributing a different piece of the puzzle. Consciousness, then, may not be a single phenomenon, but a symphony of processes, orchestrated by the hidden architecture of your brain. Let's consider another angle, the connection between memory and emotion. Why do certain memories come with such powerful emotional weight? Why can you remember exactly where you were when you heard devastating news, but forget what you had for breakfast 3 days ago? The answer lies in the amygdala, a small almond-shaped structure near the hippocampus that processes emotion. When you experience something emotionally significant, the amygdala sends signals to the hippocampus, tagging that memory as important. This interaction between the amygdala and the hippocampus is what makes emotionally charged memories so vivid and long-lasting. The four-layer structure discovered by the USC team suggests that different layers of the hippocampus may interact with the amygdala in different ways, creating a nuanced system for encoding emotional memories. This could explain why some people are more affected by emotional experiences than others. The balance of cell types in their hippocampal layers may differ, making their brains more or less sensitive to emotional input. There's also the question of individual differences. Why do some people have photographic memories while others struggle to recall basic facts? Why do some people develop Alzheimer's in their 60s while others remain sharp into their 90s? The answer may lie in the structure of the hippocampus. Genetic variations, environmental factors, and lifestyle choices all influence how the brain develops and ages. The four-layer structure discovered by the USC team provides a new framework for understanding these differences. If the thickness and distribution of these layers vary from person to person, that could explain why memory abilities differ so widely across the population. It also suggests that interventions aimed at protecting the hippocampus through diet, exercise, mental stimulation, or pharmaceuticals may need to be tailored to the specific architecture of an individual's brain. What about neuroplasticity? For years, scientists believed the adult brain was relatively fixed, unable to generate new neurons or reorganize itself significantly. That dogma has been overturned. We now know the hippocampus is one of the few brain regions capable of neurogenesis, the birth of new neurons, throughout your entire life. But this process isn't random. The four-layer structure provides a scaffold for this growth. New neurons are born in the dentate gyrus, a region that feeds into the hippocampal layers, and they integrate into existing circuits, forming new connections and strengthening old ones. This means your brain is constantly remodeling itself based on your experiences. Learn a new language, and your hippocampus adapts. Practice meditation, and the structure changes. Endure chronic stress, and the layers can shrink, become damaged. The architecture of your identity isn't static. It's a living, breathing system that responds to how you live your life. This brings us to a crucial point. You have more control over your memory architecture than you think. Studies on mindfulness meditation, for example, have shown that consistent practice increases gray matter density in the hippocampus. Participants who meditate regularly show measurable changes in the structure of this region, suggesting that focused attention and present moment awareness can literally rebuild the layers that store your memories. Similarly, aerobic exercise has been proven to stimulate neurogenesis in the hippocampus. When you run, when you swim, when you push your body, you're not just strengthening your muscles, you're fortifying the neural architecture that holds your sense of self together. The discovery of the four-layer structure gives us a more detailed map of what's changing when we engage in these practices. It's not just abstract improvement, it's the literal reconstruction of the brain's memory center. Now let's talk about childhood. Why do most people struggle to remember anything before the age of 3 or 4? This phenomenon, called childhood amnesia, has puzzled psychologists for over a century. The prevailing theory is that the hippocampus isn't fully developed in early childhood, so memories formed during this period aren't properly encoded. But the discovery of the four-layer structure adds new dimension to this explanation. If the layers develop at different rates, it's possible that early memories are encoded by only 1 or 2 layers, making them more fragile and susceptible to being overwritten as the brain matures. This would explain why childhood memories feel so different from adult memories. They're stored in a different configuration of the same structure. It also raises unsettling questions about the malleability of early identity. If the foundational memories of your childhood are incomplete or distorted because your hippocampal layers weren't fully formed, then the person you became was built on a partial foundation. Your earliest sense of self may be more fiction than fact. Let's examine another dimension: social memory. Humans are fundamentally social creatures. Our survival depends on our ability to remember faces, recognize allies, and navigate complex social hierarchies. The hippocampus doesn't just store personal experiences, it stores information about other people. When you meet someone new, when you form a friendship, when you fall in love, your hippocampus is working overtime to encode details about that person. Where you met them, what they said, how they made you feel. The four-layer structure suggests that these social memories may be processed differently than other types of memories. Some layers may specialize in facial recognition, while others encode the emotional context of relationships. This could explain why social bonds feel so powerful. They're not just abstract concepts, they're physically embedded in the architecture of your brain. And when those bonds are broken, when someone you love dies or leaves, the pain you feel isn't just emotional, it's neurological. Your brain is reorganizing itself around the absence, rewriting the layers that once held that person's place in your life. There's also the question of future prediction. Your brain doesn't just use memory to recall the past, it uses it to predict the future. Every decision you make, every action you take, is informed by past experiences stored in your hippocampus. When you choose a restaurant, your brain is pulling up memories of meals you've enjoyed or regretted. When you avoid a dangerous situation, your hippocampus is referencing past moments of fear or pain. The four-layer structure means this predictive function is more complex than we realized. Different layers may contribute different types of information to the prediction process. One layer might provide factual details, another emotional context, and still another spatial or temporal cues. Your sense of the future, then, is not a single projection. It's a composite image assembled from multiple layers of memory, each offering its own perspective on what's likely to happen next. And then there's sleep, that mysterious third of your life spent unconscious. During REM sleep, when you dream, your hippocampus is incredibly active. It's replaying the day's experiences, consolidating memories, and pruning away the irrelevant ones. But dreams aren't just memory consolidation, they're also a form of creative recombination. Your brain takes fragments of experience from different layers of your hippocampus and stitches them together into bizarre, surreal narratives. This is why dreams feel so strange yet familiar. They're built from real memories, but reassembled in ways that defy logic. The four-layer structure suggests that this recombination process may be more systematic than it appears. Each layer may contribute different elements to the dream. One provides the setting, another the characters, and still another the emotional tone. Your dreams, then, are not random chaos. They're the product of a sophisticated system working to integrate and organize the layered architecture of your mind. But what happens when the layers fail? We've talked about Alzheimer's, but there are other conditions that disrupt the hippocampus. Epilepsy, for example, often originates in the temporal lobe, where the hippocampus is located. Seizures can damage the delicate layered structure, leading to memory deficits and cognitive impairment. Post-traumatic stress disorder is another example. The constant reactivation of traumatic memories can wear down specific layers, making them hyperactive and hypersensitive. This is why PTSD patients often experience intrusive memories. The layers responsible for encoding trauma are firing continuously, unable to shut off. Depression, too, has been linked to hippocampal dysfunction. Studies show that people with chronic depression have smaller hippocampi, and the layered structure may be particularly affected. If the layers that process positive memories are damaged, it would explain why depressed individuals struggle to recall happy moments. Their brains aren't just sad, they're structurally impaired. The USC discovery also forces us to confront a darker reality. The brain can be manipulated. If memory is stored in a physical structure that can be mapped and understood, then it can also be altered. In recent years, researchers have developed techniques for implanting false memories in mice by artificially activating specific neurons in the hippocampus. The mice behave as if they remember events that never happened. This technology is still in its infancy, but the implications are staggering. If the 4 layers of the human hippocampus can be mapped in detail, it's conceivable that false memories could be implanted in humans as well, or real memories could be erased. This isn't science fiction, it's a logical extension of what we already know. And it raises terrifying ethical questions. Who gets to decide which memories are kept and which are deleted? Could governments use this technology to control populations? Could individuals use it to escape trauma or to rewrite their identities entirely? The discovery of the 4 layers brings us one step closer to a future where memory is no longer immutable, where the past can be rewritten, and where identity itself becomes a matter of choice rather than destiny. So here we are, standing at the edge of a new understanding. The 4 layers of your hippocampus are not just a curiosity. They're the foundation of everything you are. They hold your past, shape your present, and guide your future. They are fragile, vulnerable, and astonishingly beautiful. And now that we can see them, now that we understand how they work, we face a choice. Do we use this knowledge to heal, to protect, to preserve the architecture of memory? Or do we exploit it, manipulate it, bend it to our will? The answer will define not just the future of neuroscience, but the future of what it means to be human. If you found this journey into the hidden layers of identity fascinating, subscribe to the channel, hit the like button, and drop a comment with your city. I want to know where in the world you're watching from.